To analyze any circuit, you need to know how to apply mesh analysis, nodal analysis, and current division principle. Basically, if these three are known to you, then most of the circuits can be easily analyzed. So in this session, I am going to brief how to apply mesh equations so that 90% of the circuits can be easily analyzed with the help of mesh analysis. Before that, you all need to know how to apply Kirchhoff's voltage law around a closed path or around a mesh. Let us take a simple closed path and see how to apply Kirchhoff's voltage law around this mesh. For example, I am considering a closed path like this, which has several resistors and voltage sources. Suppose this is R1, R2, R3, R4. This voltage source has a value of V1 volts. This voltage source has a value of V2 volts. Imagine a current of I amperes is circulating like this, marked in the clockwise direction. This terminal, let us say A, B, C, D, A. So these are various elements in the closed path marked as A, B, C, D, A. In the mesh analysis, or when you apply KVL in any closed path, I insist you to follow a specific direction, or I insist you to follow the instruction I am giving as a rule, though it is not a rule. To avoid any mistakes in writing a KVL for a given closed path, I suggest to move yourself always along with the direction of current. Whenever you move along with the direction of current, the voltage across the resistor is always assigned positive sign. I repeat, whenever our direction matches with current direction, the sign we give to the voltage across the resistor is positive. On the other hand, whenever our direction is opposite to the current direction, the sign we give to the voltage across the resistor is negative. Though you have the choice of moving along with the direction of current or opposite to the direction of current, I always insist, suggest to write or to move along with the direction of current to avoid any mistake. So, I am moving from A going to B, B to C, C to D, D to A. This is my closed path. It means I am moving from A to B, B to C, C to D, D to A. Why am I moving from A to B, B to C, C to D, D to A? The reason is, I just now told, it is suggested to move along with the direction of current always to avoid any mistake. So, as my direction is matching with the current direction, the voltage across the resistor, which is I into R1, is given positive sign. Now the next element I am coming across on my way is a voltage source V1, positive terminal of the voltage source V1. Now the rule is, whenever you enter the positive terminal of the voltage source first, the sign of that voltage source is considered with a positive sign. On the other hand, whenever you enter the negative terminal of the voltage source first, then the sign we assign to the voltage of that source is negative. In our example, as per my direction, I entered the positive terminal of the source V1. That's why I will assign the sign of that voltage source as a positive, and the value of that voltage source is V1 volts. So I completed A to B journey. Now I am moving from B to C. The sign of the voltage across the resistor is again positive because I am moving along with the direction of current. I reached the negative terminal of the voltage source, so minus V2, then plus IR3 plus IR4 is equal to 0. According to KVL, the algebraic sum of voltages around a closed path or in a mesh is 0. That means, while writing the mesh equation or while applying KVL around a closed path, this is the basic you need to keep in mind. Always move along with the direction of current. The advantage of moving along with the direction of current is the voltage across the resistor becomes always positive. Whenever you enter positive terminal of the source first, enter the sign of that voltage as positive. Whenever you enter minus terminal of the source first, you enter that voltage as minus. That's how in this example of single mesh we moved from first one terminal to the other terminal and assigned signs to that voltage drop. Next, now let us take a two mesh network. Randomly, I am considering a two mesh circuit like this. With some numerical values for each element I considered. When you have more than one mesh, the first step in the mesh analysis is you mark currents in all the meshes. In every mesh we mark one current, either in the clockwise direction or in the anti-clockwise direction as per our choice. See here, in first mesh I marked I1. What is meant by first mesh? Any closed path in which you are marking I1 is mesh number 1. Any closed path in which you are marking I2, that is mesh number 2 for us. This example, I marked currents in the clockwise direction. If you want, you can mark both the currents in the anti-clockwise direction, one current in the clockwise direction, other current in the anti-clockwise direction, your choice. Now, how to write the mesh equations for this? See mesh number 1 equation. As I already explained, for a single mesh, it is always suggested to move along with the direction of current. So, think you started moving from one point to the other point along with the direction of current. Suppose I randomly mark A, B, C, D, A as mesh 1, carefully observe A to B. I am moving along with the current I1 direction. So I1 into 1, I1 into 1 is I1 is the voltage across AB. Now coming to BC, here you need to be very careful. See how is the status of BC? There is a resistor of 4 ohms from B to C, a current of I1 I marked like this. It is moving from top to bottom or from B to C. At the same time, look at the direction of current I2, which also is moving through the common element. But this current, as you are observing, it is moving from C to B. That means from bottom to top. The rule says whenever currents through the common element, they are in the same direction, we assign sign as a positive to the voltage across the common element. On the other hand, whenever currents through the common element, they are in the opposite direction, the sign of the voltage is considered as negative. In our case, the sign for the voltage across 4 ohms is considered as negative. Then, next observation is, as both the currents are in the opposite direction, the resultant current is difference of these two currents, because they are in the opposite directions. So the resultant current is difference. The question is whether to consider that difference current as I1 minus I2 or I2 minus I1. The rule says, while writing mesh number 1 equation, we always assume that that particular current is higher than currents of all the other meshes. I repeat, while writing mesh number 1 equation, our assumption is that current is greater than other mesh currents. Now, I am writing a mesh 1 equation. So, my assumption is I1 is greater than I2. That means the resultant current, I have to take it as I1 minus I2, not as I2 minus I1. Reason is I am writing currently mesh number 1 equation. In mesh 1, while writing mesh 1, our assumption is I1 is greater than all the other currents. That's how B to C path is completed. I repeat again, B to C, the common resistance is 4 ohms. Current I1 is moving from top to bottom. current I2 is moving from bottom to top. Both are opposing each other. That's why minus sign has come for the voltage across the resistor. Next observation is, as I am writing for mesh 1, I1 is considered as higher than other current. That's why I1 minus I2 is the resultant current into 4. Then I am at C. I am moving to D. C to D plus 5 I1. Why plus sign here? Because my direction and current direction are same. That's why plus is the sign. 5 into I1. I reached the minus terminal of the source, minus 10 volt. Then my journey is continued, plus 6 I1 is equal to 0. This is equation number 1 or mesh equation related to mesh number 1. Now let us write mesh 2 equation. Mesh 2 equation, let us say this point is E, this point is F. From which terminal we start and to which terminal we come back? See, B, E, F, C, B is our direction. What is the reason for marking our direction B, E, F, C, B? Because current I2 also is moving in that direction. As I already insisted, you always choose your direction matching to current direction. See how to apply mesh or KVL now here. Mesh equation or KVL here. 2I2, then I entered the positive terminal of the source, plus 20 plus 3I2. Now current I2, whenever, here one important point. See this is also plus, this is not minus, because as I already said, whenever we move along with the direction of current, the sign we give to the voltage across the resistor is always positive. This is also positive because of the reason I have assumed I1 is greater than the other current. So my direction is in accordance with I1 minus I2 direction. That means from top to bottom. I1 minus I2 also is moving from top to bottom. That's why this is also a plus sign. Plus 3I2, then plus 4 into, what shall I write now? Is it I1 minus I2 or I2 minus I1? As I am writing mesh 2, my assumption is I2 is greater than all the other currents. That's why it becomes I2 minus I1 is equal to 0. This is second equation. The advantage of considering your direction matching to current direction is always, every term you get positive corresponding to current into resistance. We always get positive sign corresponding to the voltage across the resistor. This is how we write the mesh equations, and after writing the mesh equations, any current you want, you can easily determine by solving the equations. There is a procedure to write the mesh equations directly in matrix form by carefully observing the circuit. So what is this method of writing the mesh equation directly in a matrix form? We discuss now by considering a simple example. I am going to write the mesh equations for this two mesh circuit directly in a matrix form. As usual, let us first mark mesh currents either in the clockwise direction or in the anti-clockwise direction as per our choice. That is the first step. After that, we are going to form R matrix, resistance matrix. The size of this matrix is 2 by 2 if there are two meshes in the given circuit. The size of this matrix is 3 by 3 matrix if there are three meshes in the given circuit. In this example, I have two meshes. That's why R matrix is a 2 by 2 matrix. First row, first column of this R matrix is simply total resistance of mesh number 1. Add all the resistances available in mesh number 1, that becomes first row, first column. Accordingly, what shall I write here? R1 plus R2 plus R3 plus R7. This is the total resistance of mesh number 1. Similarly, to write two element in this matrix, second row, second column simply indicate the total resistance available in mesh number 2, that is R3 plus R4 plus R5 plus R6. This becomes the total resistance of mesh number 2. All the resistances available in the closed path of 2 or mesh number 2 are considered here, R3 plus R4 plus R5 plus R6. Accordingly, this element 2, 2 is marked here. Now coming to first row, second column, 1, 2 means the resistance common to meshes 1 and 2, that common resistance has to be entered with appropriate sign. That means you need to know when to enter with a positive sign and when to enter with negative sign. Look at the directions of the currents in the common elements. I1 according to the considered direction, it is moving from top to bottom. How is I2 moving? I2, as per the direction I marked, it is moving from bottom to top. Whenever currents in the common element, they are in the opposite directions, we enter that element, that resistance with a minus sign. In this example, as currents are in the opposite direction, I am entering that with a minus sign. The resistance common to 1 and 2 meshes. There is no difference between 2, 1 and 1, 2. That's why this is also minus R3. Suppose, example, I have a resistor R3 and you marked currents like this. Mesh directions, mesh currents, directions are like this marked by you. Now look at the situation. In the common resistance, both the currents are in the same direction. If this is the situation, I enter the element with a positive sign because currents are moving in the same direction. But in our given example, as the currents are in the opposite direction, we entered it with a minus sign. R matrix into I matrix. I matrix means currents. Simply I1, I2 is equal to voltage matrix. After all, V is equal to I into R. Accordingly, R matrix into I matrix is equal to V matrix. Now see how to fill the V matrix. Mesh number 1. If your direction is from minus terminal to plus terminal, or if you are entering the minus terminal in that mesh first, reverse the polarity, minus becomes a plus here. See mesh number 1, I am entering a minus of the source. When you take that minus to the other side, it becomes a plus. So I am entering the first element simply as plus V1. In mesh number 2, I am entering plus terminal of V2. Plus terminal of V2, when you take plus to the other side, it becomes minus. So the V matrix is, second mesh is minus V2. Hence I repeat once again, while considering the V matrix, the rule is, if you are entering minus terminal of the source while moving in your direction, enter that voltage source terminal as positive in this matrix. When you enter positive terminal of the source, take it to the other side, it becomes negative. That's how we fill the V matrix and R matrix. Let us practice another example by developing the R matrix, V matrix confidently. For this example, you become perfect in writing the mesh equations in matrix form. So randomly I am considering an example. And let us see how to write mesh equations in a matrix form for this circuit. Randomly I am marking the sources and resistors are marked with resistances. These are all the various resistances and various voltage sources of the given circuit. What is the first step I explained while applying mesh analysis? First step is mark mesh currents either in the clockwise direction or in the anti-clockwise direction as per your choice. See, as I observed 3 meshes, I marked 3 mesh currents as per my choice. I1 is in the clockwise direction, I2 is in the anti-clockwise direction, again I3 I marked in the clockwise direction. Now my goal is to write mesh equations in matrix form. So let us construct the R matrix. What is the size of this R matrix? The size of this matrix is 3 by 3. Reason is there are 3 meshes, so the matrix is 3 by 3. How to write first row, first column? Sum of all the resistances sum of all the resistances of mesh number 1. Add all the resistances of mesh 1, what will you get? R1 plus R8 plus R5 plus R6 is the first row, first column. Then how to write the second row, second column? Sum of resistances of mesh number 2. Do it. R2 plus R3 plus R4 plus R8. Then what is the third row, third column? Sum of resistances of third mesh. So R1 plus R2 plus R9 plus R7. There are 4 resistances in mesh number 3. Any order you write, immaterial, all are added. R1 plus R2 plus R9 plus R7. Now first row's second column, 1, 2, element 1, 2. What do you mean by element 1, 2? The resistance common to meshes 1 and 2 with appropriate sign. So R8 is the common resistance about the sign. How is I1 moving through R8? It is moving from top to bottom. How is I2 moving in R8? It is also moving from top to bottom. As currents through the common element, they are in the same direction. In this example, the sign of R8 is considered as a positive. There is no difference between 1, 2 and 2, 1. Now coming to 1, 3, first row, third column. 1, 3 means the resistance common to meshes 1 and 3. What is that resistance common to 1 and 3? It is nothing but R1. Now what about the sign of this voltage across R1? Look at the direction of I1 through R1. It is moving from left to right. And what is the direction of I3 in R1? It is moving from right to left. As both the currents are in the opposite direction, 1, 3 is taken with a minus sign. There is no difference between 1, 3 and 3, 1. This is the matrix. Minus R1. Now what about 2, 3 or 3, 2? Resistance common to 2 and 3. What is that resistance? R2. What is the sign? Sign has to be positive because I3 is moving from right to left. I2 also is moving from right to left through R2. So through the common resistance for 2 and 3, both the currents are in the same direction. That's why it is entered with a positive sign. That's how the R matrix is developed. And as I already explained, I matrix means simply I1, I2, I3. So R matrix into I matrix is equal to V matrix. Now look at V matrix mesh number 1. You move yourself along with the mesh and write various voltages with appropriate signs. Now in mesh number 1, I entered plus terminal of V2. Obviously, when you enter plus terminal for V2, when you take it to the other side, it becomes minus V2. Then you reached minus terminal of V1. Take it to the other side, it becomes positive. That is mesh number 1 voltage. Now coming to mesh number 2 voltage, you reached plus terminal of V2, so this becomes minus V2. You reached plus terminal of V3, so it becomes minus V3 on the other side. Now coming to mesh number 3, you entered plus terminal of V4, so it becomes minus V4. This is how we develop the mesh equations in matrix form while writing the mesh equations. What is the advantage of writing the mesh equations in matrix form? For example, a particular circuit randomly I have written mesh equations in a matrix form like this, just randomly for a given circuit. I have written the mesh equations like this. The advantage of writing mesh equations in matrix form is I can determine the unknown currents by straight away applying Cramer's rule to the mesh equations available in matrix form. What is Cramer's rule? To get I1, replace the first column of the R matrix with the V matrix column. See, I want I1, so the first column of R matrix is replaced with voltage matrix, and I am not disturbing the other columns of the R matrix, divided by determinant of R matrix. This is what Cramer's rule is. Suppose I want I2. How to get it? Don't disturb the first column of R matrix. This is as it is. I am not disturbing the first column of R matrix. As I want I2, second column of R matrix is replaced with voltage matrix, and the determinant of R matrix as it is. That's how we determine the unknown currents once the equations are available in matrix form. I'll take another example. See this, randomly some 3 by 3 matrix equations are given to you. For a given 3 mesh circuit, imagine I got the mesh equations like this: R matrix into I matrix is equal to V matrix. Suppose I want I3. How to get it from this? Don't disturb the first 2 columns of R matrix, because I am interested in getting I3, which is belonging to the third column. Replace that third column of R matrix with the voltage matrix divided by the resistance matrix determinant of R matrix 1, 4, 7, 2, 5, 8, 3, 6, 9. So this is what? Current I3. Like that, any current in the mesh can be determined, in any of the meshes can be determined by applying a tool, very useful tool known as mesh analysis. Most of the circuits can be analyzed by applying mesh analysis to that network.